Okay, perfect. So good morning or good afternoon, everyone. Welcome to this colloquium at not the usual time, but there are always constraints in life, and we try to fiddle around them. Yeah. So it's very nice to see that we have many people, as many people online as we have in person. That's really very nice. And this morning, I'm very pleased to introduce to you Professor Marco Merkli. Marco and I go back many years and have some joint traditions that we won't explain here, because otherwise our reputation will be affected. Marco is originally from Switzerland, but he's a professor of mathematics and statistics at the Memorial University in St. John's, which is in Newfoundland. I know that there's a slide on that.
Yes.
So I won't say anything about that. He just finished teaching a course at Ames, and that's why we were lucky to convince him to come for a day or two to Stellenbosch. Yeah. So Marco, please, you know how it works.
I will figure it out.
Okay, just the arrow.
Thanks so much. It's a great pleasure to be here. As Francesco said, I just taught at Ames Musenberg for 3 weeks, of course, in quantum theory. And I'm very glad to be able to come here. It's my first time in Stellenbosch. It's my third time in South Africa, but my first time here. And it's an amazingly beautiful place today. So I think you're lucky to be here. Can I maybe minimize this, or does this influence anybody online? And I have to, I'm very sorry to correct Francesco. I'm only a professor of mathematics, not of statistics. It's just that our department is mathematics and statistics together. Okay, so nope. How do I go forward?
We need to touch this screen, and then it should work.
Okay. That's okay. So you are probably not aware of the existence of the place where I live. The city is called St. John's, and it's not exactly centrally located in Canada, as you can see. So here's the US with the States, here's Canada, this huge country with the provinces. And at the very east coast, you have the province called Newfoundland and Labrador. It's not very visible here. Should I maybe lower the lights here? Yeah. Okay. Anyway, so Newfoundland and Labrador is the part here. This is Quebec. And then this here part is Labrador, and Newfoundland is an island here. It's a big island. It's a huge island. It's maybe as big as 6 or 7 times Switzerland where I grew up. Anyway, so there is the capital is called St. John's, and its population is about 200,000 inhabitants. So it's relatively small, and it's rather far away from here. Okay, so it's about 12,000 kilometers. Of course, if you can fly directly like this, that would be great, but an actual trip is a little longer because you have to go first to Europe and then down to South Africa. Okay. When I left, so we are in the Northern Hemisphere, right? We're up here. And when I left about 4 weeks ago, it looked like that. This was after we had a little snowstorm. So it can snow quite heavily where we live. It's actually on the sea, and it can snow, and the snow gets blown and accumulated. So you can have hip-height snow accumulations. It's fun. When I showed this picture at Ames, to the students there, and most of them have not seen snow, of course. And they were horrified. And afterwards, some people came to me and said, "But if you go outside here without gloves, your hands just fall off, right?" I said, "No, it's not that bad." Okay. In fact, our temperatures are rather moderate because we are on the seashore. In the winter, it's around 0, and so we do get often quite a bit of snow, but then it also melts quickly again. Okay. So that was about 4 weeks ago. About 4 months ago, it looked like that. So again, we have a natural harbor. That's our waterfront here, and sort of the city is known to be kind of cute and have these modern houses with different colors and little streets and stuff like that. And when you go outside of the city, you have a lot of nice landscapes with skies and sea and windswept plains and things like that. So my university is called Memorial University, and we had about 19,000 students. I checked it out yesterday compared with Stellenbosch. You have about 29,000, so your university is about a third bigger than ours. We have did I do this correct? No, I'm not sure anymore. We have about 4,300 graduate students and less, so I think the proportions are a bit different. Okay, and we have quite a number of international students at our university. In fact, our university is sort of interested in building up relations with institutions worldwide, and they asked me to present to you this possibility of student exchanges. So there's this organization in Canada, it's called MyTax. It's a non-profit national organization, a Canadian one, and they would like to foster international research collaborations between Canada and the world. And in particular, there's many programs and grants that you can apply for, but there is in particular this Global Link Research Award. This is for students, for undergraduate students, or graduate students, or postdoctoral students. And the idea is that you would get some money, and you have to apply for this with a project, and you will get some money to do a little project, say within your PhD or within your postdoc, that will be supervised jointly with a faculty member here and a faculty member in Canada. And so you get a bit of money to travel, and that could be a nice possibility. Okay, so now I would like to come to the scientific part, I guess, and talk about open systems and give you an overview. I don't really quite know your background. I mean, I know that Francesco is one of the experts, of course, in open quantum systems. And so what I'm going to talk about is really rather basic. And at least in the first half, and in the second half, I'm going to talk a little bit about some recent work I did, which is less well known for you maybe. And so that gets a little more specific, but everything is going to be non-technical. Okay, and it's silly a bit that I talk about open quantum systems being here, right? Because maybe you know the Bible about open quantum systems. And I thought maybe, Francesco, you could come and continue the talk because, because this is the reference, right? And everything I'm saying, except for the last part, is of course, much better explained actually in this book. So what is an open quantum system? It's a quantum system which interacts with some external quantum system, which is called an environment or a path. And oftentimes, you know, if you have a system, you decide who is the environment and who is the system of interest. And a system that is in contact with its environment is called open. Schematically, right? This is a picture, you have your system, and it's cut to several other systems. You can see there's many of those gray ones, there's only one system of interest. That will be a common feature sort of that distinguishes the environment from the system itself. And they pop up everywhere in these systems. Here's a picture, well, I mean a schematic picture of the structure of light harvesting complexes in plant cells. These are responsible for carrying out photosynthesis in plants. And you can't really read it well, but there's from 1 up to 8 sites where you have special atoms that can capture sunlight, absorb sunlight, get excited, and then transfer the excitation along this complicated structure called this protein scaffold. The excitations, quantum excitations get propagated along a very complicated structure and go into what's called reaction center of a cell. In the plant, and there it does chemical reactions and produces useful things for the plant to grow. Anyway, in all kinds of quantum theory, in real life, systems are open because you could have these 8 these 8 sites here, that would be, for example, your system, and you would want to see how do they propagate excitations, and there's lots of influence from all kinds of outside agents that act on that, and you want to understand how does this work. So no quantum system is really completely isolated from its surroundings, right? And being quantum systems and being rather fickle, interactions with anything can significantly change the dynamics. And so obviously there's a need to have a theoretical framework for describing open system dynamics. And as I said, in all kinds of quantum theories, quantum optics, quantum information, chemistry, and biology, these open systems play a big role. So here again is a system that will be what you're interested in. It exchanges whatever energy, mass, information with its surroundings. For example, a qubit, right? Register mounted on a substrate, or many things like that. And the main question in this topic is how does the coupling to the reservoir affect the system dynamics alone? So you kind of want to figure out what's an effective evolution of the system alone that is influenced by the reservoir coupling. And just think about it. So this is a sort of a billiard situation that looks kind of classical, I guess it's classical. But let's say you have 2 boxes, a system box and the reservoir box, and they interact in the sense that there's a tunnel between these 2 boxes. And you put a particle in the system box and you give it a kick, and then the particle scatters around, and eventually it will find its way into the reservoir part. And so if I'm only looking at what's happening in the system, then I see, well, after a certain time, oops, the particle is gone, okay? Because it went over here. And I can only look at this. And then, of course, when the particle is over here, it bounces around and eventually gets propagated back. And so my particle comes back. And so I have this back and forth. And this is kind of an oscillatory kind of evolution, right? If I only restrict my U to the system alone. Of course, the particle is always somewhere, but if I restrict myself to viewing only this part, the particle is here or not in a time periodic sort of way. But what if the system and the reservoir are not equal partners, sort of? That's this picture here, where my reservoir now is much, much bigger. If I start off with my particle in here, then, oh yeah, after a while it will have propagated out. But because this reservoir is huge, I will have to wait for a very long time for the particle to come back to my system that I can observe. And so you can imagine that if one part of this system reservoir complex, maybe the reservoir part is very huge, this forces sort of the dynamics of the system part to be, you know, almost, how should I say, irreversible. Because in the limit, when I take an infinitely extended reservoir here, then once the particle escapes here, it doesn't come back. And I have infinite dynamics or decay probabilities or whatever, as opposed to this situation where the system and the reservoir are of equal size.
What happens if the reservoir has same type of particles and almost infinitely many of them? Could there be interactions between those with the initial particle and one of the particle from the reservoir then it's then another particle that comes back into the system?
Yes, that's absolutely possible. Yes, if you have very, very many particles here, of course you could have a lot of influx and still something non-trivial happening here all the time. But I would say usually what you do in this instance is you look at the system only. It is very complicated. In fact, this usually has infinite many particles. It's a very complicated state, maybe a thermal state or something like that. And here you look at energy transitions, for example, that are constantly influenced by the reservoir part. But the point is sort of once the system gives something to the reservoir, this dissipation doesn't come back. So information flows away, even though different noise information from the system constantly influences of the reservoir constantly influences the system. So, I mean, if you have done basic quantum theory, then you also know these two, right? And this is the same kind of thing as before. Before it was kind of classical billiard type. But if you take 2 spins and they interact in a way that they can exchange energy, and you times 0, you excite. Let's say you can put 1 excitation in this coupled spin system. let's say you put it here, the excitation at time 0, and then you let the two spins evolve, and then you calculate what's the probability of finding the excitation still at spin number 1. If you make this easy calculation, you see that it's a sinusoidal curve. It is periodic. Excitations moves back and forth between these two equally big partners. Okay, this is oscillation. But you also know that if you have now another spin or a qubit or a two-level system that could mimic, for example, an atom with an excited state and a ground state, and you start getting up in the excited state and you place it in a very big system, the quantized electromagnetic field, this yellow part here, then what happens is that the atom gets de-excited. It goes from excited to the ground state, it emits a photon, and the photon never comes back and re-excites the atom. So the probability of excitation of the atom decays typically exponentially and goes to 0. So again, decay or irreversibility versus oscillation. Why? Because one part of the system is huge. Of course, if I look at totally where is the excitation, well, it will always be somewhere. So the fact that we get this decay to something disappearing is only because we look at part of the system or locally. Okay. So how do you derive these things from the basic fundamental equations of quantum theory, which is the Schrödinger equation? Okay, well, you know the Schrödinger equation, here it is. It can be written in integrated form if you wish, right? So the propagator applied to the initial state. But so the question is, what is psi here? And psi is, the answer is psi is the state of a closed system. This equation is valid for closed systems. Okay, you know that, well, I mean, this is also visible because H itself, the energy is a constant of motion. So the total system doesn't lose energy. The energy can be transferred between different parts of the system, but the total energy is conserved. So the Schrödinger equation is valid for a closed system. Okay, I know this is easy. Look at the qubit. State vector is in C2. Let's say this is the Hamiltonian, the Pauli Z matrix, and then I can calculate the evolution. And what do I see? Well, how do I do this? I look at eigenvectors and eigenvalues of the Hamiltonian, and I write the propagator in this spectral form. And what I see though is that, well, as a function of time, this is just periodic or maybe quasi-periodic, right? These eigenvalues of these Hermitian matrix are real. So I get these phase factors and everything just oscillates. Yeah, I have just motion that's quasi-periodic. Nothing is going to decay here. Okay, well, that's an easy system. Let's make it a bit more complicated. How about we couple this thing, this spin, to a bunch of oscillators, which could then be modeling an environment. So here is the spin or the qubit. Here is n oscillators, the creation operators A, K, and AK. And this is a coupling term. This term annihilates an oscillator mode, and it creates an excitation in the spin. And this does the opposite. And you know, whatever you know how to describe this, these are eigenfunctions of this eigen of this Hamiltonian and so on. And you can do the same thing. You can write the propagator here in terms of just its spectral, you know, projections onto the eigenfunctions, time the corresponding exponentiated eigenvalues here. E, and J's are the eigenvalues of H. What do you see? This stuff is periodic. I mean, you know, okay, there are infinitely many terms because of course now sort of the dimension is infinite, right? Because each oscillator has infinitely many energy levels, and you have n oscillators, you could have infinitely many oscillators, who cares? But the point is that the spectrum of this thing is just eigenvalues. And so when I look at the propagator, it's just really a function that's quasi-periodic in time. No decay. So how do you get decay? Well, you remember probably from what's it called? The scattering theory, that bound states are associated with eigenstates of Hamiltonians, and scattering states, which are states that, well, scatter away, right? That is kind of irreversible. they are associated or eigenstates that are maybe not normalizable or something with spectral points that are not eigenvalues of the Hamiltonian, but they lie in the continuous spectrum of H. And you also remember, probably, that if you have a confined quantum system, then the energies are discrete, just discrete values. And the extended system, so a system that's, let's say in R3, a particle in R3, whose Hamiltonian is given by the Laplacian, the spectrum of that is continuous. Okay? And so the general motto, I guess, around here is that if you take a larger and larger reservoir in an open system, so that's part of this open, I mean, that's the part the open system is coupled to, then by increasing the volume, the energy differences between next neighbor eigenvalues of the Hamiltonian become smaller and smaller. And in the thermodynamic limit, when you take the extent, the size of the volume to infinity, then the eigenvalues, they become continuous spectrum of the corresponding Hamiltonian. And once you have that, you're not confined anymore. You have continuous spectrum, and locally irreversible dynamics becomes possible. Is there? Okay, so maybe I can do that quickly, because even for people who are experts in open systems, maybe they're not so familiar with that. So maybe I can quickly say something about this thermodynamic limit. So the question will be, okay, how do I actually construct an infinitely extended, let's say, reservoir of particles, free quantum particles, but infinitely extended? Okay, so you do the thermodynamic limit. You start off with a box with finite volume, side lengths, let's say L. If this is position space here, it's maybe centered at 0, let's say. And you imagine that at 0 here, you have your system. And then the reservoir is this yellow part, which is this box, and the idea is to take the box larger and larger until you take V to infinity, then you would have a really, truly spatially extended reservoir. Okay, so when you put the box, let's say, electromagnetic field or particles or modes into the box, because the box, well, is finite, it's compact, right? The energies are quantized, they take values. And you know from basic quantum theory, actually, the difference between two different momentum or energy eigenvalues behaves like 1 over L to the power 3 in 3 dimensions, where L is the size of the box. So the spacing of eigenvalues decreases as L increases. And as I said, sort of in limit V goes to infinity, the spacing between eigenvalues collapses, and discrete spectrum turns into continuous spectrum. So what you would do is the following. I would place in this box, take a fixed V, place in this box a density rho j of particles having momentum kj. So I'm going to select for a fixed V, I have my energy spectrum. I select a bunch of modes I would like to populate this box with. How many? Well, first of all, I choose, let's say, n modes. I want to create modes k1 up to kn. And each of those, I want to create how many particles, the density, corresponding density times the volume. That's the number of particles I create in the mode k1, and so on. So I just apply creation operators to the vacuum, and so I populate in this box. I build a state that has this momentum density distribution. And then I'm going to increase V, and as I increase V, the K moves, right? Because they depend on the size of the box. And if I can take V bigger and bigger, then the Ks, again, they sort of coagulate into a continuous curve, and you can play the following game. Let's give yourself a continuous target momentum density distribution of the state you want to build. And then you approximate with finite volume approximation, you approximate this density distribution with finite modes. And then you build the state, as I said above, with these finite modes, and then you make V go to infinity, and you can ask yourself what happens in the limit when it goes to infinity. That's the infinite with volume limit. And the problem is, of course, for each finite V, you can just write down this guy. I guess this should also be normalized and write this. But you have a vacuum, so the other space has more and more particles, but whatever, right? But when you try to take V to infinity, you will see that you cannot do this on this vector. I mean, you don't even know what kind of Hilbert space this should be in as you take V to infinity. But the point is that physical quantities have a good limit as the volume goes to infinity. The mathematical state vector does not. But that's okay. So what you can see is that averages of observables in this state, when V goes to infinity, have a good limit. And you can calculate that limit. And so what you end up with in the thermodynamic limit is not a state in the usual way. It is a functional. This means volume infinity. It's a functional that does the following. It's like a black box, and it does the following. If you want to know what the average of a local observable is, you feed this functional this local observable, and it spits out the average value of your local observable. So this describes the infinitely extended system in terms of averages of any observable you like. Okay, but in this process, as V goes to infinity, you have lost the notion of Hilbert space, because all you end up with is really this function. There's no more Hilbert space here. And if you want to do any kind of analysis, then you sometimes need to have a Hilbert space. And then it's very interesting that you can use techniques from operator algebras, which is a mathematical theory, to reconstruct the Hilbert space. So this you have calculated, but you have lost the notion of Hilbert space. But now, the operator algebras come and say, oh, I can rebuild a Hilbert space for you in which I can express your functional as if it came from a vector, right? Because the expectation usually is given by the inner product of state vector times the observable. So you can actually do that, and you can actually do that explicitly. And the first time this was done was by Araki and Woods in the early 60s. And this is all explicit. You get explicit formulas for everything. And so just what I'm trying to say is that you can write down a simple model, simple explicit model, where you actually have a reservoir which is infinitely extended. Okay, and then you can play around with that. Then you can play this, you can couple this to your qubits and see what's going on. Okay. So we're interested in dynamics, and now we are always assuming that we have a infinitely extended reservoir and that you have a localized system S. The system is usually just, a system having a few degrees of freedom, having a few energies, possible energies, being finite dimension, like an n-dimensional system. It has its Hamiltonian, reservoir has its Hamiltonian, and then you have a coupling strength. This is the general interaction, that's the general sort of setup of the structure of a Hamiltonian of the total system and reservoir complex. And here you probably can't read it, but I just recopied the spin coupled to the bosonic degrees of freedom, which is kind of a very standard model people look at. Okay, and then the evolution of the total system and reservoir is given by this Hamiltonian. And here I'm talking about density matrices now. When you look at open systems, you have to talk about density matrices because states don't stay pure anyway. So you have an initial density matrix of the system and reservoir, and it gets evolved according to the Schrödinger equation. You have to multiply it with the propagator from the left and the right. And then most often you're just interested in the system state alone. And how do you get the system state alone? Well, you have to take the full state of system plus reservoir, and you have to take the marginal. You have to trace out. You have to take the partial trace over the reservoir of this operator that acts on system and reservoir. What you end up is with the defective or reduced density matrix of the system alone. And really, what you would like to do is to have a good equation for this system density matrix alone. You see, this equation here, whatever this will follow as an equation, will be kind of complicated because this Hamiltonian here has built-in the interaction between system and reservoir. So that's complicated. And one of the problems is that even if initially at time 0, you have a system state times a reservoir state for the combined system, that is where the system and reservoir are not entangled, they are uncorrelated. Because in the dynamics, you have interaction between the two, the dynamical map, which would be sort of the flow, saying to this initial system state, I associate the system state at time t. So this map is not of Hamiltonian form. That is, I cannot find possibly any kind of operator effective Hamiltonian, so that I would apply this to the initial system state and get the system state at time t. This group structure of the dynamics is not correct because of the interaction of system and reservoir. Okay, and this is true because of memory effects. You see, such an equation here is how should I say, of Markovian form. So if your evolution was like this, then propagating from time 0 to time 100 seconds would be the same as going first from time 0 to 10 seconds and then from 10 seconds to 100 seconds. That would be Markovian, but this is not the case because of correlations that build up due to the interaction between the system and reservoir. And if you don't have this structure, you don't have the notion of an effective Hamiltonian, you cannot try to use, I mean, you have to ask yourself, what kind of techniques can I use to sort of know something about this? And usual techniques, which would consist in diagonalizing this guy and then figuring out, you know, bound states, scattering states, whatever, cannot be used. Okay? So before I will show you that in many instances, something like this is still correct, approximately. That's called the Markovian approximation. But before I do that, I thought I would show you a few generic dynamical effects that happen due to the interaction with a reservoir. And one that you know is called thermalization. So suppose that initially your system is in any kind of state, and the reservoir is expected, this very huge, large system is in thermal equilibrium. So this is a reservoir, and this is beta, that's the inverse temperature. Suppose it's in thermal equilibrium or close to that. And then what thermalization says is the following. If I look at the system dynamics alone, so the system density measures at time t, and away from quite a bit of time, I will be driven to some final state for the system. What is this final state? It's of the form e to the minus beta h prime. And h prime is some system Hamiltonian. It's called the mean force skip state. And it can be viewed as a renormalized system Hamiltonian that incorporates the interaction with the reservoir. In fact, if, let me go quickly back here. There's this lambda. Oftentimes people have to do perturbation theory. This would be the uncoupled situation, then this is the situation with coupling. So lambda is coupling constant. So oftentimes people do theory for lambda small. And if you do that kind of theory for lambda small in the thermalization business, then it turns out that this effective or final Hamiltonian or mean force skip state is actually the original system Hamiltonian plus corrections, as I said, that are due to the interaction with the reservoir. You can calculate this determinant in any kind of order. Okay, but you see something here, right? So apparently you may talk about small coupling and large time. So there are two sort of limits involved, right? Lambda to 0 would be small coupling, times to infinity would be large times. But of course, it's important for this to happen to first take t large and then lambda small to get this kind of situation. If I take first lambda small, if I set lambda to 0, the system will just have its own evolution. It will just keep oscillating, not decaying, not being driven to some final state, even for time goes to infinity. So it is not correct that you can invert orders of limits in this business. Okay. Another effect that people often talk about, you probably have heard about it, is decoherence. This is a thing that happens independently of thermalization. Of course, thermalization happens if the reservoir to begin with is sort of close to thermal equilibrium, right? But even if you take different reservoirs, different kinds of models for noises, decoherence still happens. And people say decoherence is the following. For large times, the reduced system state becomes a diagonal matrix in the energy basis, okay? Whatever that means. But the point is that the interaction with the environment destroys coherences, which would be off-diagonal matrix elements. And if you interpret this in terms of quantum theory and quantum computing in particular, this is a loss of quantum properties, and it's detrimental to a good implementation of quantum computation algorithms. Okay, so this open system noise is an impediment to the working of a quantum computer. And here's another one. That's the third one. Generic effect, sort of, it's suppression of entanglement. So the motto is environment destroys entanglement. I took this picture here from a very nice paper by you and Averly. These are quantum optics guys, pretty famous ones. And they did the following theoretical experiment, okay? You take two cavities, cavity A and cavity B, and in each cavity you put an atom, atom A, atom B. And each atom is just modeled by a two-level system, so spin, cubic. And these cavities, they do not talk to each other. There's no interaction term in the Hamiltonian between these two systems A and B, okay? Atom A interacts with cavity A, there's a mode there, and atom B interacts with cavity B. Nothing else talks to each other. But initially, you take a state in which atom A and atom B are entangled. Just in the initial state, there is this quantum entanglement. And then you let the dynamics evolve. And what they see is the following when they look at the entanglement of atom A and atom B as it moves as a function of time. Well, initially you started off with entanglement maximal, which is 1. And then because of the interaction with the reservoirs, the entanglement of the two atoms decays. And it decays to 0 in some finite time. This is a point of sudden death of entanglement. And then if you wait a little longer, whoops, suddenly the entanglement between the two atoms comes back a little bit in an attenuated form, but it still comes back and then it dies again, comes back and dies again, and so on. So this is amazing because, because these two systems don't talk to each other. And the reservoirs don't talk to each other directly. Only via the initial entanglement between atom A and atom B, these two parts talk to each other, and yet you get this destruction of entanglement, right? I mean, it's like I have a system here and one over there, totally separated. My reservoir here and my reservoir there, they don't talk to each other, and yet entanglement gets destroyed. This is again bad for quantum information theory because you need entanglement for making quantum information processes work well. Okay, so now I plan to talk about the Markovian approximation. We can check the time. And the setup is as usual. You have an open system reservoir Hamiltonian, system part, reservoir part, an interaction operator, and this interaction operator carries in front of the coupling parameter. This happens on a bipartite system, reservoir empty space. The reservoir is big, the system is small, finite dimensional. The Schrödinger dynamics of the full system reservoir density matrix is given by the initial guy, then propagated according to the Hamiltonian. The reduced density matrix of the system alone is obtained by tracing out the degrees of freedom of the reservoir. So this is the partial trace of the reservoir degrees of freedom. And then one should talk about two kinds of initial states. Either the initial state of the system and reservoir, that's this guy before you start propagation, is of unentangled form, so product form, a system state tensor a reservoir state, that you will call an uncorrelated initial state. And a correlated initial state would be, well, something that's not of this form. And it makes a difference in terms of mathematics and physics, which one of these two situations you start off with. And actually, if you go and look at the literature on open quantum systems, which is humongous, I would say 95%, even more, 98% of situations, people look at uncorrelated initial states and check out what happens for this. So if you look at uncorrelated initial states, once again at time 0, these are disentangled, then it makes sense to introduce a mapping which maps the initial system state to its state at time t. Okay. And as we said before, this mapping is well defined, but it's not it doesn't have this effective Hamiltonian group form, okay, because entanglement gets generated between system and Hamiltonian. And then the big question is, well, under what kind of circumstances can we approximate this map VT, which is the flux of the dynamics, if you wish, mapping the initial state to the state of time t? Under what circumstances is this a group or a semi-group? In other words, when can I write this kind of like that? Where here L would be what physicists call the super operator, this L acts on the density matrix, right? Because if I would stick the initial state here, I would get the state at time t of the system. Okay. Why would you even want to do that, right? Well, you would want to do that because if this is a good approximation, you have a lot of tools at your disposal as to how to analyze the dynamics. You would, for example, just go and diagonalize this L, and you would find, real eigenvalues or imaginary eigenvalues stuff. You would find fluctuating stuff, you find decaying stuff, and so on. So these tools could be used to analyze the dynamics. And people do the following. They say, all right, let's start off with a reservoir, which is under its own dynamics in a stationary state. Okay? And the reservoir is huge. And the interaction with the small system is kind of not so big. So they would say, let's make the first approximation. It's called the Born approximation. My reservoir just does not feel the interaction with the system at all. So my first approximation is that the total system reservoir state at time t actually looks like that. The reservoir just doesn't move. Plausible, I guess. And then they say, okay, fine. So now I only have to deal with this kind of dynamics. The reservoir part is gone. That's usually a much easier situation because that's usually finite dimension. The whole thing's infinite dimensional, whatever. And then they say, okay, but this is still complicated. Let's make another approximation. Let's sort of make an approximation where the reservoir loses memory quickly. You can write down formulas as to what this means. And if you say that, then you can say, okay, in this case, this dynamics actually, that's this guy here. This dynamics can be written in a Markovian form, in just such a way as I said before. And if all this works out, and you can or cannot justify these approximations, and you say, okay, I just look at this now as my evolution equation in differential form. This is just the derivative of the state, is the operator L applied to the state. Sorry, it's a typo, this should not be the initial state, this should be type P. And this is, of course, the ubiquitous master equation that everybody uses. But so this was when you started off with uncorrelated initial states. Of course, right? If t is equal to 0, you can see that you already assume that this is sort of uncorrelated. So what happens if the initial state is correlated? Okay, if the initial state is correlated, well, quantum dynamics doesn't care if it's correlated or not. The principle is still you have the initial state. This is the total state at time t. I have to take the partial trace to get the state of the system. Okay, so this formula is still correct. But I cannot even start this other procedure because the Born approximation obviously is wrong. Because for small times, I'm not a product. Time equals 0, I'm not a product. Also, for small times, it's certainly also not a product. So I can't even start with this approximation. And it's even worse because it turns out you cannot even define a map that maps the initial system states to its system state at time t, because you see, you can have the same initial state of the system alone, but having different correlations with the reservoir. And because the correlation also plays a role in the dynamics, you would have for the same initial state, you would have at a later time 2 different evolutions because the correlations were different. So I cannot even define this map initial state for the system of the system to a system state at time t. So none of this works. Okay. And so then it's a quarter 2, right? Am I seeing that right? Yes. So I have still 5 or 10 minutes or so. So then I wrote this ingenious paper. No, but seriously, I was trying to see what happens. What can one say about correlated initial states, and I would like to show you what I did in this recent paper, sort of. Okay, and the model is the following. As usual, you have an n-level system coupled to some bath. Okay, if you want to know, you have Hilbert space, like the Poisson Fock space, and so on. And then you have Hamiltonian of the system and one of the reservoir and an interaction term. And I want to look at initial states that are either correlated or not correlated. And I want to take initial states though where the reservoir is at least spatially asymptotically. So you remember it's taken to be a spatially infinitely extended system. But if I go very, very far out spatially, it should be an equilibrium state at temperature T. Okay. And I will give you the Hamiltonian exactly. So the n-level system has eigenfunctions phi and eigenvectors E. And this is usual bosonic field operator. And the interaction we take to be linear in creation and annihilation operators. Okay. So field quanta are created and annihilated, and this induced by some operating G transitions in the in between different energy levels in the small system. Maybe the details are not so important here. There are 2 specific states. So the Gibbs state of the system is the density matrix, which is e to the minus beta HS. HS is the density matrix. And as I said, for the infinitely extended reservoir, you have a state which is not really a density. I mean, it is a density matrix, sort of, but in a different space, whatever. But it tells you that, according to Planck's law of black body radiation, the average in this state, so this state is called omega, and the average of A star K A L, where K and L are 2 momenta in R3, right, is proportional to 1 over e to the beta omega minus 1. So that's Planck's law of black body radiation. Beta is the inverse temperature. Let me not talk about the initial states. They can be correlated. Let me not talk about the assumptions. We can talk about this if you feel like it. But let me talk about what we can do. And this is actually, I mean, the model is kind of simple, I guess, but the result is material, so it's provable. Okay, so you have an initial system reservoir state given by a density matrix, possibly correlated, possibly uncorrelated. You don't really care. And the other player is the system marginal, so the reduced density matrix of the system alone. That's the initial reduced density matrix of the system alone. It's obtained by taking the full initial state and then taking the partial trace of the reservoir. And then we look at coupling lambda, which is small but fixed. It's perturbation theory. And we derive a result that's correct for all times bigger than or equal to 0. And what does the result say? It tells you about the dynamics of the full system and reservoir complex. That's the full state at time t. It has 3 parts. It has a blue part, a green part, and an orange part. The blue part is a Markovian term. You see that this is a state of system plus reservoir, which is disentangled because it's a product form. On the reservoir, you're just in the thermal equilibrium. And on the system, you are in some state which depends on time. And it has this Markovian form because it's given by a semi-group e to the PL. L is some operator, some super operator acting on the initial state. Remember, this is the initial state of the system alone. So in this term alone, the reservoir is in its equilibrium state, and this guy, the system, evolves according to Markovian evolution. Then there's another part, which is a correlation term. I will describe in more detail in a bit. And then there is a part which is a remainder. And this is small for small coupling. This constant coupling, constant small. And one of the good things is that this is small, no matter how large or small time is. This is the uniform estimate of time. Okay, So the Markovian dynamics, you can calculate what this super operator or effective Hamiltonian, I guess, is of the system. And it has a free part, which will be the dynamics given in absence of the interaction with the reservoir. And then it has order lambda squared, an order lambda squared correction term. Okay. And if you look at the spectrum of this thing here, this is not a Hermitian operator, but the spectrum of this guy up here looks like this. It's on the left real axis. So imagine the real part is only negative, and it can have imaginary part positive or negative. And you see the direction here, the horizontal direction, the real part gives decay, because look, if I stick in one of these eigenvalues here in this formula, I would have e to the t times a complex number, but this complex number has a negative real part, so that drives decay. And it may also have an imaginary part, which also drives some oscillation. Okay, but there's nothing that explodes in time, luckily, because no eigenvalues are positive in real part. There can be, and there is usually, under very generic assumptions, an eigenvalue at 0 of this operator here. And this eigenvalue of 0 would yield a contribution here, which is projection onto a stationary state. Okay. Then there is this correlation term. This has to be there, right? Because if initially you start with a correlated initial state, this cannot be the correct dynamics, not even up to this order of correction, right? So this has to be there. And this takes care of initial and at all times correlations. And this term actually vanishes if you start initially in the product state. So then the dynamics is really given by that. But if initially you have correlations, that guy is not 0, of course. And also, if you're only interested in the evolution of the system of variables alone, this here state, this part of the state will disappear. Because the initial correlations on the system alone are encoded already in this guy here. Okay. And another thing you can prove is that this thing here decays in time. This decays in time like 1 over the power t, 1 over t to the power 3, because we are kind of in 3 dimensions. And it decays in time polynomially and at a rate which is independent of the interaction between the system and the reservoir. These are facts. We'll put all these facts together right away in a few corollaries. And here are the corollaries. I have about 3 slides left or so. So this is the first corollary. It says that the Markovian approximation for these kinds of systems is valid for all times. So if you have initially uncorrelated states, the dynamical map makes sense. You can compare the dynamical map to this approximating dynamical map, which is a semigroup, which is Markovian. And for all times, this is less than a constant times coupling constant to lambda 1/4. Okay. These results on a mathematical term were known, but not for all times, that they hold for all times. It was only known with so-called ultra-weak coupling limit. We can discuss it if you want, but this was sort of new that this can be shown to hold for all times, for a fixed lambda for all times. Okay. A corollary is also that yes, in this situation, for this kind of initial states, of course, the Born approximation is actually valid, because it is true that the dynamics of the whole complex looks like this Markovian part. Correlations are 0 here, and a small remainder. So the Born approximation is shown to be valid here, up to an order of small in the interaction. And when you look at correlated initial states, oops, that's of course a gross mistake. Copy and pasted. So this should not have product form. Okay. Then you see that actually the Markovian approximation is also valid for correlated initial states. This formula just stays valid. The initial correlations, once again, are just built in here, but you can use the same generator to propagate, to use this approximation here Markovian approximation, even for initially correlated states. And corollary 4, it's maybe, I guess, the most interesting. It says something about the system plus reservoir dynamics, both of them, not just the system alone. Okay. So correlations at the beginning may be large because you see at time equals 0. This is 0. So the chi, modulo this other term, drop this, drop that. Chi is the difference of the initial state with the uncorrelated part, system tensor reservoir. Okay. Anyway, that's written here. And so this could be large if I start off with the system reservoir initial states, which is not close to this because that's correlations, then this chi will be large for small times. Okay. But as I said, it becomes polynomial in time at a speed which does not care about the interaction of system and reservoir, because the decay of the correlation really moves to the fact that the system dynamics alone is dispersive. So if you move the system locally somewhere and you just let the system dynamics evolve, the perturbation sort of goes away to infinity, spatial infinity, at a characteristic rate. Whether you couple to a small system or not doesn't matter. So this is driven just by the free system reservoir dynamics, so to speak. So if I put this all together, right? So I have these two terms. I want to compare now who is bigger, right? Correlations or the Markovian approximation. Okay, so blue terms versus green term. And this is the Markovian part, is the correlation part. This decays like 1 over t to the power 3, independently of lambda. This decays like, remember this picture, sorry for the scrolling. This picture here, I mean, check it out, okay? So when lambda is 0, this thing has eigenvalues that lie all on the imaginary axis, okay? But then if I switch on lambda, these eigenvalues move away from the imaginary axis and acquire a negative real part. How much? Well, by an amount of lambda squared. So all these distances up to the left here are of the order lambda squared. So this gives decay rates of e to the minus t times lambda squared. Okay, so lambda squared is kind of the decay rate. And so that's why whatever decay happens here happens at a speed of 1 over lambda squared, which depends on lambda, of course, while the other dude didn't depend on lambda. This here doesn't depend on that. Okay, so then the picture emerges that you start off with a lot of correlation initially. This here decays much more quickly than this exponential if lambda is small. Okay, lambda small means that the system is driven slowly to its final state. So the curve associated to this dynamics is almost not moving in time as that if lambda is small. And the correlations decay quickly. So eventually there will be a point where the correlations are below the Markovian approximation. And that's when the Born approximation and the Markov approximation become valid. And after that, the Markovian approximation becomes valid. Okay. When this happens, you can calculate. It depends on what the initial states is, what the correlations are initially. It even depends on what kind of observable you look at, but you have expressions for this thing. Okay, so the message is, even if you have initial correlations, because of the infinite volume of the reservoir, they dissipate, and after a certain time, the Markovian approximation just becomes valid again. Et voilà le résumé. We have a finite system coupled to a thermal quantum field. We use an expansion of the system plus reservoir dynamics together in a part which is just projecting onto the reservoir thermal state, and a part which is orthogonal to that, plus a small remainder, valid for all times. And we can show that the Markovian approximation for the system dynamics is valid for all times, even for initially correlated states. And we can show that the Born approximation, which is a statement that's about system plus reservoir dynamics, this Born approximation is also valid, of course, for all times if you start uncorrelated. And if the initial state is correlated, it becomes valid after a certain time. It can actually be calculated. Okay, now I have to really concentrate because I would like to. Danke für Ihr Belangstellung.
very much, Marco, for a very, very nice talk and for sharing new interesting results.